Well, we can't hear you.
How about now? Ah, good. Damn, those problem-solving videos have no audio. That sucks. I'll have to go and look at that. That probably means I have to remake them. Oh well. They get better every time I make them, so it's mostly just a time issue. Okay. So let me make sure I have the recording going. Okay. So yeah, so we've been talking about acid-base chemistry, and so I was saying that the overarching goal for most of these problems, or I guess the overarching goal a lot of times for the problems, not all the time, is that we're trying to find the pH of a solution. And so we have the basic problem, which is, you're given a strong acid or a strong base, and you're asked to find the pH of that solution. Things get a little bit harder when you are finding the pH of a weak acid or a weak base solution. And then we added on this other layer of neutralization reactions, which just is an extra step before you find the pH of a solution. Yeah, fundamentally for those problems, fundamentally at the core of all of those problems, though, we're just trying to find the pH, and the problem gets trickier when you're trying to deal with weak acids and weak bases because you have equilibrium going on, and you have to make a lot of like sort of estimates of what's going to contribute to the pH and et cetera, and that can get a little bit confusing. So the best way to get good at these, this is true of all of the course, but especially for this one, is to work lots and lots of problems. So you get used to a lot of these weird cases. So we looked at neutralization. Let's take a look at what happens. There's something called the common ion effect. And it really falls out of what we learned about Le Chatelier's principle. If we look at a problem, I think I actually maybe work this one in office hours. But if you look at a problem where we have hydrofluoric acid, and we're going back and forth, or at equilibrium with that in fluoride, we're sort of familiar with, or hopefully by this point, if you're given a specific concentration and we're given the Ka of this, then we can look at what the pH of this solution is going to be. What we haven't discussed yet, so normally what we're talking about is we'll give you a concentration of one conspecies. So for example, the acid, and say, what is the pH of a solution of 1 molar hydrofluoric acid once it comes to equilibrium? Then you go through and you do this Rice table. But you could also make a solution where you have, for example, you could start out, let me write a problem out for it. Say like, what let me not write in script. I know, showing my age, I don't even know that they teach script anymore. What is the pH of a 1 molar solution of HF and 1 molar, let's say, sodium fluoride. What is the pH of a 1 molar solution of HF and 1 molar solution of sodium fluoride? I think that's generally how these are phrased. So usually when they're given like this, right, the concentrations that you're given, yeah, cursive. Sorry, I don't know. I grew up outside of New Orleans. They say weird stuff. Maybe scripted and cursive are not the, script is not the common way of saying it. We also use the term like elementary school and grammar school. I don't know. I think we use grammar school and I don't know. Anyway, I'm getting off. And we also, instead of calling them counties, we call them parishes in Louisiana. It's a weird ass state. They use Napoleonic code for law. So sometimes I say stuff. I also have like an accent I'm always constantly working against. I can't pronounce like ORs very well. It's like the word mirror really messes with me. I want to say Mira from the way I grew up. Or error. I don't know. Anyway, I'm fighting my southern roots. All right, anyway, I'm way off topic now. So what is the pH of 1 molar solution of HF and 1 molar sodium fluoride? So what is special about this problem is that typically we're starting with just the acid and we're saying, okay, you know, we're making a solution of acid. What's ultimately going to be our hydronium concentration? And so that's how we figure out our pH. But here, what's unique is that we're starting out with some acid, but we're also, before we even start the reaction, we've dissolved up some, this is some of the, so hold on, some of the acid. We have 1 molar HF, but before we even kind of let the thing come to equilibrium, we've already added some of its conjugate base in. So you'll notice I've written, I know this is a point of confusion, so hopefully you work through these problems in the handouts. You'll notice sodium is here. The sodium is a spectator ion. You can just act like it doesn't even do anything. All of the group 1 metals are just spectators. And so if you see a group 1 metal, group 1 cations, they're always spectator. For acid base. So if you're looking at these salt problems and you're trying to figure them out, if you have something from group 1, it's not doing anything. Sodium, potassium, these are the common ones that just don't do anything. So in your mind, this is what you can think about for this. This is really F minus, right? So that's what sodium fluoride really is. Just like sodium hydroxide, who really cares about the sodium? It's really hydroxide, right? So you can just disregard those. So anyway, so then I can go and say, okay, well, like, how would I work this out? And you set it up essentially in the same way that you set up your other problems, which is that we set up one of these rice tables, say, okay, what's the reaction? What changes here is that our initial concentration is different. So usually you're just putting your initial concentration on the right-hand side of the equation. We'd say, okay, we're starting out with 1 molar HF, and then we're going to figure out the equilibrium concentrations. But here, because we have sodium fluoride, which again is just fluoride, I'm also starting out with 1 molar of that. And so then I go through, that's the only thing that changes at this point. Then I go through and I represent my changes as the same thing. I say, okay, well, I'm going to lose some amount of HF. I'm going to gain, we start with 0 at that. We're going to gain some amount of H plus, and I'm also going to gain some amount of F minus. And I can write out my equilibrium concentrations here as 1 minus X, X, and 1 plus X. And then again, I just solve. I go through and solve this the normal way. I would write out my mass action expression for this, which is the Ka expression. And then I can plug in some values here. So I could say, so I've given Ka up at the top here. Say, okay, well, 7.2 times 10 to the minus fourth then is going to equal, and I start plugging in my values here. So I have hf, that's 1 minus x, h plus is x, f minus is plus x. Oops. And then I want to solve this thing. So this equilibrium constant here is very small. So small is less than 1. Really, like, we'll say less than 10 is pretty small. So if that equilibrium constant is less than 10, what this means is not much product forms. We know this from our equilibrium chapter that for equilibrium less than 1, it's reactant favored. And for equilibrium where K is greater than 1, it's product favored. But I'm just making a point of it here that less than 10, let's say, you're really getting very little product that forms at all. And so we can use this to our advantage. If we know that not a lot of product is forming, then we know that 1 plus x and 1 minus x are generally going to be extremely small. Are generally going to equal approximately 1. And so I know this approximation gets a little bit confusing because there's so much crap going on in this problem. But think about it like this. So we're starting out with 1 molar HF. And all we're saying is, X down here, this number, let me switch out of my ink pen here. This number, whatever we're losing here, once we come to equilibrium, we know that this is going to be a small number because 7.2 times 10 to the minus fourth is less than 10. That means that not a lot of HF is going to dissociate to form H plus and F minus. So 1 minus some extremely small number is going to be approximately 1. I compare it to 10 instead of, sorry, let me finish this. Somebody's got a question. So 1 minus x is going to be approximately 1, and 1 plus x, for the same arguments that I just made over here, which you're going to pick up, is going to also be small, because that's whatever you lost over here. It's also going to be small, and that's going to be a plus 1. So the assumption I'm making is that x is going to be some really tiny number. And when I say tiny, I mean like x times is going to be like 0.00001. And so you can imagine that if it was if x was 0.00001, right, that's not going to change my value of the starting concentrations by very much. And that's why this approximation works. So why do we compare it with 10 instead of 1? At 1, you have 50% product and reactant for K. So you don't really have a predominant species there. You probably can't get away with the approximation. Less than 10, I think, just from what we were going over in office hours, thinking about it, you start to get to the point where you have a pretty big, you have a very small amount that goes to the products. You could sort of fictitiously work problems with different equilibrium constants to see where the approximation fails. But I think once you get less than 10 is when the approximation starts to get pretty good for K. So that's why instead of 1. 1 is like you're right in the middle. You're getting a good amount of product forming. Why do we have an initial 1 molar of fluorine? I think you mean fluoride. We have an initial amount of fluoride because that's what the problem is dealing with. We're looking at the situation here where instead of just making a solution where we have hydrofluoric acid at the beginning, instead of just having hydrofluoric acid, I'm saying, well, what if instead of adding hydrofluoric acid to a flask, I also add in sodium fluoride? And so this is an important, it seems like an arbitrary thing to do, but it actually turns out to have a bunch of different consequences, which we're going to see. Okay, so anyway, so we can do this approximation. So I'm doing this approximation. I'm saying 7.2 times 10 to the minus fourth is equal to 1 times x over 1. And so that tells us what x is. That's equal to 7.2 times 10 to the minus fourth. So is x a very small number? Yes, x is. So if you come back and check your approximation over here and say, well, you know, is this true? Well, yeah, what's 1 minus 0.00072? Yeah, that really is approximately 1. You're not really subtracting much out there. Yeah, at k equals 10, there is a lot of product. I'm sorry, at k equals 10, there's not that much product. So it's case specific, right? So the k values, sorry, I'm not trying to throw you guys off with this metric here. It's just a rule of thumb. I'm saying once k gets to be less than 10, you're not forming much product. And the smaller that number gets, the less product you form. But naturally, it's going to depend on a lot of things. For one, it's going to be dictated by the stoichiometry of the reaction is going to play a role in it. Why are we approximating for both? Man, these approximations are always messy for people. Why are we approximating for both products values and reactants values? We're not really, the approximation has very little to do with chemistry. It has more to do with just math. And the math of the situation is just saying, all we're saying is, like, I'm looking at this number. When I'm doing this approximation, I'm looking at this number. I'm saying k is very small. And then I'm saying this means x is very small. And since I know x is very small, I come and I can just look at expressions, regardless of what's going on with the chemistry, like 1 plus x, and say, well, if x is really small, then probably 1 plus x is basically going to be 1, because x is going to be very close to 0. And the same is true of 1 minus x. So x is a tiny number. So I can say that these are approximately equal to 1. Like, why don't I just set this equal to 0 as well? Well, that approximation doesn't hold any there. It only holds when you're adding something to x that's much larger than x, or subtracting it. So if I'm adding or subtracting x from some large number, well, then I can just approximate that thing to be the large number. But if x is by itself, well, then you have to count x, because x is, there's nothing to say it's small relative to. It's a relative thing. I know it's confusing. I'm sorry. You do not have to approximate. So if you have so for example, if you know how to use like Mathematica or Python or something, and you can solve mathematical equations super fast, then you can just plug all this crap into one of those types of things and just solve it every time and be fine. You should get 2 answers for most of these. You should end up with at least a square term, if not a cube term. But that's a way to solve these, and that's perfectly, especially since we're doing these online, it's perfectly acceptable. And honestly, at some point, I feel like somebody's going to have to update the curriculum to reflect the fact that we have computers and we can use those to solve equations. Mathway is good. Okay, I'm not familiar with that. Learn Python for chemistry. Yeah, don't learn Python for for this. But there's lots of solvers out there. I mean, I think even like a TI-83 or something can solve this. It's been a while since I've messed with that kind of stuff because I'm old. But I think even Excel solver you could use to solve this. But anyway, learn the approximations. The approximations are good ways to think about. Well, I'm saying that in terms of just doing well in the test, yeah, plug it into a solver if that makes it easier for you. Looks like somebody posted a resource for solving equations. But in terms of trying to like kind of get a handle on the chemistry, these types of approximations are easier. If you go in and take analytical chemistry at UT, which I don't, unless you're going into chemistry or you're taking it as an elective, it's a really interesting class, analytical chemistry. I actually get to apply a lot of this stuff. You'll work on equilibrium in more detail, so those approximations, you'll get a second shot at learning them. All right, anyway, all right, so we've gotten blown way off course here. So yes, so the approximation and the Rice tables I know is the most confusing part, but it really is just algebra. And I'm not saying that to trivialize it. I'm just saying like try not to, I think a big problem that students have is, you know, obviously these things are tied to the chemistry, like where X is related to, we're trying to solve ultimately for the concentration of HF. But ultimately, a lot of this crap just comes down to just some algebra type stuff. And there's a confusion, I think, between when we're doing algebra and when we're actually like doing something that's related to chemistry. And this over here is an algebra type thing. This is like a trick to solve this equation that we're doing. Okay, so anyway, so we end up with this. The reactants always be negative in a Rice table? Good question. No, the reactants, well, you mean in terms of what X should be equal to, minus or plus? Yeah. You can use signs either way. You could put a plus here and minus on the other side. It doesn't matter. You'll get the right answer. It just makes it more confusing. The reactants are not always negative. If you wanted to know which direction the reaction, yeah, it depends on Q. Excellent, Madison. If you really wanted to know whether you were going in the forward or the reverse direction, you would calculate Q, and that would tell you the direction that which direction you needed to go in to get to equilibrium. Very good, Madison. So no, so the short answer to your question, Chloe, is no, the reactants are not always negative in the Rice table, but it makes logical sense to think about them as being negative, depending on which direction you're going in. So if you're going to the right, it makes sense to think about losing something. So that's why we just minus X. But because it's math and the signs are just arbitrary, if you made this a plus and made these minuses and worked through the problem, you get the same answer. You should get the same answer. Okay, so anyway, so what do we find here is we've solved this for X, and we see that our pH for this is then going to be equal to the negative log of 7.2 times 10 to the minus fourth.
Gillian, teach us.
I'll take the PhD, but I won't teach you. We're learning acids and bases. You should know this. What is there to tell? I'm sitting outside. Y'all want to watch squirrels? Okay. They're kind of far, but like, I don't know if y'all can see. Okay. That's enough. Oh.
Small salad. I'll take a double, triple bossy to this on a wrap. 4x4 animal style. And fishing goes with the shimmy and the squeeze. Like absolute grease making crime. Burn it and let it swim.
All right, well, that was an unplanned intermission. Yeah, I don't know. My computer crashed and then just really didn't want to get back on Zoom. Yeah, sorry guys, I don't set your tuition. I know it sucks that you're paying thousands of dollars for it. That wasn't a Wi-Fi issue. That was my MacBook Pro just freaking out and just I've actually never seen it do that. It just stopped working and then shut down and then just rebooted. Hopefully that doesn't happen again. Thank you, Gillian, for picking up the slack.
You're welcome.
You still can't hear?
We can. I think it's an individual problem. We can't.
Oh, so bad squirrels. You guys are funny. Squirrels will be on anything Gillian taught is Kanan now. That'll be on the exam. Yeah, maybe it's I think the operating system just updated. So maybe because my MacBook Pro is older. I don't know. All right, so anyway, stepping back in as if like 10 minutes haven't passed in between this. Recording can be weird for the, oh, it is recording. Okay, stepping back in, we end up, so remember we were taking HF and we were doing this problem where we start out with some F minus and we have some HF and we end up with a pH here that's equal to 3.14. If we compare this to the other situation, let's say where we take HF, if we just take HF, and let's say we're starting out with a different concentration with a normal sort of problem where we don't have 1 molar. Wait. Why do we plug 7.2? Yeah, that's what X is equal to. So yeah, so I know it's confusing. What is X? So we solve for X here. And then when you want to figure out what the pH is, you come up here and you look at what we assign for the value of H plus. We call it H plus X. And so that is literally this value. And then I just take the pH as the negative log of H plus. So remember, it was the Ka. So here, just coincidentally, Ka was equal to the hydronium concentration. And that works out because we set the initial concentrations to 1 molar. Basically, any other concentration would have given us a different number, but it makes the math really easy. Yeah, just coincidence. Okay, so if we work the problem, if we work another problem, so like let's say that we're working this problem where we don't put any sodium fluoride in initially, we would work it out the same way. Naturally, the mass action expression is the same. Everything that we did at the top is the same. So we'd end up with an expression of x squared minus 1 minus x equals 7.2 times 10 to the minus 4th. And we could solve this for x. And we should end up with 2.7 times 10 to the minus second. So I'm skipping some steps here because this is a problem we should know how to do. And so we'd end up with our pH equal to the log. Our pH is equal to 1.56. So let's compare these. So X, which is really equal to the H plus concentration, is equal to 2.7 times 10 to the minus second if I start out with 1 molar HF with no sodium fluoride. But it's equal to 7.2 times 10 to the minus 4th, a smaller number, if I start out with 1 molar HF and 1 molar of F minus. So what we see is that if we start with products there, it suppresses the amount of HS that dissociates. F is a different problem. This is for comparison. So let's say, let me put it this way. So for this problem, where our initial concentrations are this, we end up with a pH equal to 3.14. If we work a different problem, where our initial concentrations are this, we end up with a pH equal to 1.56. This corresponds to a hydronium concentration of 2.7 times 10 to the minus second. And this corresponds to a hydronium concentration of 7.2 times 10 to the minus fourth. And so what we see is that we can affect the amount of acid that dissociates. You can approximate it in the second one. You can approximate it down here. 1 minus x is still just approximately 1, I think. I just skipped the solving of it. You can use the quadratic if you want. All right, so the lesson here, I know the approximations are confusing and that just takes work. But put that aside if that's confusing for you for now. And let's look at something else. Let's talk about the chemistry of the situation. So the interesting result here is that if I start with fluoride in solution, I form less H plus than if I start with no fluoride in solution. And so remember when we talked about Le Chatelier's principle, we said that if you add product, what do we expect to happen to the equilibrium? It should shift back towards the reactants. And that's exactly what we're seeing here. We're seeing that if we add some fluoride in initially, because of Le Chatelier's principles, or really because we're tied to the equilibrium constant through our mass action expression, we end up forming a lot less H plus at equilibrium. So without any fluoride, we form more H plus, so we get a lower pH. So if I were to continue to increase this number, like let's say put 2 molar, 3 molar, 4 molar, I would form less and less H plus there. Because the more product that's present at the start of the reaction, the more it suppresses sort of the dissociation of whatever you add to solution. So one way to think about it, if you're trying to kind of visualize it, is if I take a solution, like let's say I have a beaker. So I have beakers. If I have pure water here, and then over here, I have a solution of sodium fluoride, and let's just call it fluoride just to avoid any confusion there. So we have a solution of F minus. You couldn't, it doesn't matter. I was going to say you can't have just F minus, right? It has to be electrically neutral, the solution there. But so over here we have a solution of F minus, and I add in the same amount of HF, the pH, even though I'm adding even though I'm adding 1 molar HF to both of these. So I'm taking and I'm dissolving in the exact same amount of acid into both of these. Here I end up with a pH of 1.56. And here I end up with a pH equal to 3.14. If I were to take an increase, the addition of, it's not that the addition of sodium, well, the addition of sodium fluoride does make it more basic, but the key thing to take away, the way to generalize it is that the addition of any product that's going to appear in the equilibrium expression So if we have this equilibrium expression here, if I add in F minus, that's going to change my concentration of HF. Because remember that K is constant, so something has to give, right? K isn't going to change. And so less HF dissociates because I have more F minus present. That's really the main lesson. HF is a weak acid. Yeah, this is only for equilibrium. So so it has to be something that's at equilibrium for this to matter. So it wouldn't matter for like HCl, for example. This wouldn't make a difference. Or I don't think I don't think you could make a difference in any reasonable concentration of chloride. So this is called the common ion effect. There's names for all these different types of things, but they really all fall out of this. So like whenever you're like trying to figure out the hell's going on, if you want to return to whatever our first principles are, you look at the mass action expression. That's really our go-to thing here. The common ion effect. It's a different flavor of Le Chatelier's principle, which is that if you add a product, it pushes things back towards the reactants. That's exactly what we've seen here. We've added a products. And so now we're going to form, so now we're going to form, in a sense, we're going to form more reactants here. You could try, I mean, you could work the problem out differently where you could say, like, if I start out with 1 molar HF and let it come to equilibrium and then add in fluoride, you will see that the pH decreases as you add, increases as you add in fluoride because you're going to shift the reaction back towards here. Okay. Another way of looking at it in like kind of a blunter way is just that ultimately our concentration of H plus, one way to think about it is ultimately our concentration of H plus is dictated by this equation here. So you almost always we're solving for H plus as our unknown. So if I start out with some concentration of HF, that's going to give me one value of H plus. So like, I guess if I start out with one concentration of HF and 0 and some other concentration of F minus, like if I change these two numbers, that will change this number. So when you're solving this equation, the starting concentrations of HF and F minus matter. And usually, like the way we've looked at things is we're just starting out with 0 F minus, but you don't have to do that. You could start out with some there. That's what we're doing here. And so it's not surprising if you look at your expression for K that our H plus concentration ultimately has to change to accommodate that. So K is constant. These things can vary and be a lot of different things, and changing one or changing two of them will affect whatever this is. So I guess what I would say is if intuitively it makes sense that if you assume that F minus is 0 and that I take HF and I say 1 molar versus 2 molar versus 3 molar, that's going to affect our pH. Right, if I just change the concentration of HF, let's say I'm in this problem over here. If I were to change this to 2 molar, you're going to expect that to affect the pH. If I change it to 3 molar, you're going to expect that to affect the pH. And that makes sense, I think, intuitively, because this is an acid, and as I add more acid, I'm going to expect the pH to drop. But in the same way that adding this affects what our pH is, adding something over here also can affect our pH. So another way to look at it is that this is an acid and this is a base. In this case, I'm adding in acid, so I'm adding in only acid. So I'm expecting this to drop down to a low pH. If I add in both acid and base, I'm expecting the pH not to change as much. So the addition of any product to greater the pH. No, that's not exactly right. Yeah, that's not exactly right because we could add in H plus here, right, and that would drop the pH. The lesson here is just that if I add in products, less of this dissociates. That's a general idea behind equilibria here. In acid-base chemistry, usually what you're adding in is this common ion or whatever over here. That's the conjugate base of the acid, and that pushes things back to the reactants. The same would go for the complete opposite. If HF was replaced by a weak base and NaF was replaced by a weak acid, the pH would go down. That is correct. So if there are more products, less reactants react. That's not exactly how I would put it, but yeah, I think that's true. Oh shit, it's 9:53. Yeah, right, because I had a 10-minute interim where I had technical difficulties. On Friday, we'll cover buffers, which is what I was hoping to get to today. So all of what we're talking about here leads to buffers, and we're look specifically at this guy or these guys who somehow got their name attached to this equation, Henderson-Hasselbalch equation, which sounds intimidating because these guys have long names that sound, I don't know, maybe European. At least Hasselbalch does. But in the end, it actually makes things easier. So we'll look at buffers. And maybe titrations, but definitely buffers. Yep. Okay. All right, let me take a quick break, an actual break where I'm not just scrambling, plugging things into my computer. And then I'll see you guys in a second in our normal office hours. And we can chat more. Okay.
I had a question, if you don't mind us starting.
Okay. Let's get going it up, Cyrus. Do you guys have any specific questions?
Yeah, I had a question about the equation. Sorry, I forgot what the name was called. The one you said we were gonna talk about next class.
Henderson-Hasselbalch equation is just a, if you look in the GChem website under the buffer section, I haven't looked at that. But I'm almost positive they have that on there. It's just the pH for a buffer solution is equal to the negative, it's equal to the pKa minus, is it plus or minus? I have to derive it. Plus or minus.
We can't see what you're typing.
Minus the log. I gotta look it up. It's been a while since I've used the damn thing. So you can derive this pretty quickly from the sign on it depends on the how you write the logarithm. That's why I'm pH equals plus. I got the sign wrong. I have a feeling. You can write it as minus if you flip HA into the numerator. Okay.
It
See
was
the
more.
screen. Yeah, why is that? Where did my screen go? Oh, okay, there we go. Right. I forgot for Zoom, the screen has to be in the front. There we go. Oh, that's a great technical problem today. All right, so yeah, Henderson-Hasselbalch equations. Yeah.
Yeah,
You can ask a quick question on the Henderson-Hasselbalch equation. We'll go over it formally in class.
Yeah, sorry. It's not like more. It's not about like what it actually is. It's more of like when you're solving like these like.
So this is the Henderson-Hasselbalch equation. It's specifically for buffers.
Right. Yeah. For
We haven't actually defined what a buffer is yet, so that's not super useful to you. But buffers are when you have an acid base conjugate pair present. So for example, in the last reaction that we worked, I don't want to get into stuff there because we're going to cover this on Monday, but not on Monday, on Friday. But the last problem we worked, this is the acid, this is its conjugate base, so it's a conjugate base pair. So you could also calculate the pH using this equation, which is easier, obviously, than using a Rice table. Christine, what was your more general question?
Oh yeah, sorry. It was more of like for these buffers questions. Like technically, if you can use the Henderson's equation.
You would take the negative log of 7.2 minus fourth, and then you could add in the log of so here your pH would actually equal your pKa. Which would be 3.14. So it's just that you can see it, that takes a lot faster. Yeah, neutralization problems are good. We'll get into this on Friday. I'll try and after office hours have a meeting, but after that I'll try and remember to post some problems. There's a good buffer kind of preparation worksheet on the GChem website. I think in the extra practice problems that I'll post.
Should we do the LE for buffers before
it's ready
Friday
for
or
this.
after Friday?
Can we just do some? Yeah, I can make up neutralization problems, but I'm trying to think of a good way to teach them, because I know they're getting a little bit confusing. It seems like I feel like the main problem with acid-base chemistry is that
No.
it's like hard to know. It's like hard to know like when and what you're dealing with problem-wise, like depending on how the problem's asked. Like, is it a neutralization problem? Like, do I use a rice table? Do I not have to use a rice table? Where can I make approximations? Oh, I don't hear you guys. Is my audio messed up? Maybe, oh, you know what? I don't think my headset reconnected. Yep.
Boo.
Okay, now I can hear you. All right. Speak away.
I was wondering if we should do the LE for buffers before Friday or after.
Oh, I can't remember what's in the LEs. In my mind, they're supposed to be like simple introductions. I can look at it real quick. It's not, if you can work, I would just go through it and just work it before Friday. It's probably better. The more prepped you can come into class, like the easier it is to kind of follow and get something out of it. That's what I think of the LEs as being good for. They're good to just kind of like introduce the material, so you're not just seeing it for the first time. Yeah, even the first question is, in our next class, we'll discuss buffer solutions. So yeah, definitely do it beforehand.
Oh, my previous question about the Henderson's equation, sorry, it was like more of a general question. Like
Yeah, go ahead.
when we're going through like these buffer problems, technically if you're able to use the equation, shouldn't you be also able to like solve it like the long way, like using rice tables and stuff like that?
That's correct. Yeah. Yeah. So the Henderson-Hasselbalch equation is a shortcut.
Right, because I was looking at this website that was like solving a similar problem to the homework, and then like one of the comments was like AP chemistry teacher saying he tries to have his kids use it the long way because then they don't. It's just kind of like an automatic plug-in for them using the Henderson's equation, and like they wouldn't really understand the overall like
Concept of it.
aspect of it, right? So
Yeah, I can see the rationale for that. I mean, the reason that, I think the thing that becomes challenging with the Henderson-Hasselbalch equation is like knowing when you cannot use it. That's usually the trickiest thing. It's the one of the reasons to teach it here is because you end up using it. I'm pretty sure they use it in biochemistry a good amount, the Henderson-Hasselbalch equation. I guess I would say, practically speaking, in terms of like what you might actually use in life, if anything from this course, making a buffer is pretty common, like across most of the natural sciences. Maybe not physics, but so knowing how to use the Henderson-Hasselbalch equation is useful for that. I don't know. I've never really thought about whether it has what the like pedagogical utility of it is. I guess for me, I just feel like it's just a straightforward way to calculate the pH for a buffer solution. I remember when I took general chemistry, I would just derive it every time just for practice. But obviously, it's my major was chemistry, so I was kind of nerding out and interested in stuff. So if you want to work it out the long way, you can. But it is so much faster, or it is significantly faster, I guess, to just work it out. Especially when you're working through titrations and stuff, it's significantly faster to just work it out with the Henderson-Hasselbalch equation. So your call, Christine. But yeah, but to your point, I guess what I would say is like, I don't even know why these guys get their names attached to this equation. It's not like some huge it's not like for example, like the Schrodinger equation or something where, this guy pulled this equation for quantum mechanics out of thin air and really deserves his name attached to it. All they did was take and rearrange some shit and take the logarithm of it. It's not like any kind of special thing. It really is, like you're saying, just a natural extension of the way that we normally solve equilibrium. So it's not like some super special thing. As long as you get the right answer, though, you're good. If you want to solve it the long way, that's fine. Yeah, neutralization problems. We can work some more neutralization problems. I mean, I think the main thing with neutralization is just to is to make sure you break up the problem appropriately. And I think I'm probably rushing through the first part too fast, so the classic, like a not advanced problem, would be to say, like, what is the concentration of HCl, NaOH, and NaCl. Where's the concentration? Or how, I guess I'm trying to think of how we would phrase it in a general chemistry course. We would probably say, how much, let me just start over. How much HCl and NaOH are left over so this would be like so the difference between, I guess, like, this would be a normal question in like chemistry 301 or something. We might give you the reaction. So in the acid-base chemistry section, you're kind of expected to be able to write out the reaction here. So you say, okay, well, I know HCl is an acid and sodium hydroxide is a base, and that those are going to react. They must always form a salt. And frequently form water. And so that would be our reaction. And then we would work from this to figure out the how much, just the final, whatever you want to call it, the final products or whatever, like it's a limiting reagent problem. And so this is for strong acid, strong base, that would be, but it doesn't change. So, there's all this confusing crap in the acid-base section where it's like we got strong acids, we got weak acids, we got all this different stuff. And when do I use equilibrium constants, etc. The neutralization reactions are the one place where it's like semi-uniform as far as what you need to worry about, at least initially. You know, so like we could say similarly, like how much and it can get more complicated than this, I'm sure, like most things do. How much acetic acid and sodium hydroxide remain after the reaction of, 1.6 moles and how much sodium acetate would be the other reaction, and just water. I don't care about that. And so again, you would just write out your general S. You'd say, okay, this is my acid. And this is my base. And I know that acids and bases react. The acetic acid will lose a proton and become, getting ahead of myself in my head. So I just write those out as is on the reactant side. I don't have to do anything fancy. And then over here, we have to consider like where, what's going to happen between these things. So there's going to be a proton transfer between the acetic acid and the hydroxide here. So this is going to pop off, and it's going to connect into the base, which is the hydroxide, to form water. And then I have water over here, which I don't care about. And so those are the starting points for your neutralization reactions. If you can get through this part, though, then the next part becomes just the stuff that we've been learning about. That's when you have to start kind of letting the new acid-base chemistry kind of kick in. So how would we solve this? So I guess the one nice thing about, like the one thing that makes the neutralization piece easier for acid-base chemistry compared to 301, the thing that makes it harder is it's lumped in with a bunch of other crap. The thing that makes it easier, though, is that we're typically going to give you things in terms of moles, and the stoichiometry is typically going to be straightforward, 1 to 1, 1 to 2, that kind of stuff. So you're never given like, in general chemistry, we'll ask you to convert things into like, we'll give you grams and ask you to convert it to like number of atoms or number of molecules and stuff. And this is not that fancy, but it is at its heart just a limiting reagent type problem. So you'd say, okay, well, I would recommend trying to do these by analysis a lot of the times, but you can look at the amount of base that you have. And you can look at the amount of acid you have. And then you just come down here and you look at your reaction, and you can kind of, without having to do any math, figure out all the different, without having to do any kind of like really fancy math, you can kind of figure out all the final concentration, especially for this one where everything's 1 to 1. So remember that the chemical reaction here, right? This is just a recipe. This is just a recipe for making sodium chloride and water, if you want to think about it that way. And all it tells you is that for every molecule of HCl I have, I need 1 molecule of sodium hydroxide, and that allows me to make sodium chloride. So if I wanted to make 10 molecules of sodium chloride, or let's work in moles, which is essentially the same, you can think about it in the same way. It's just like a set number of molecules. If I wanted to make 10 moles of sodium chloride, I would need to go to my pantry and get 10 moles of HCl, and I'd also need to get 10 moles of sodium hydroxide. So right, you can think about like I've got a stock room, so I've got a chemical stock room. So this is my stock room. And that's just like a pantry where I keep things. I keep chemicals. And so I go in there and I have a certain amount of moles of HCl and a certain amount of moles of sodium hydroxide. Okay, so now instead of thinking about it in terms of like a normal recipe, so, like a normal recipe, like let's say if you're trying to make, let's say that you're given the task of going and making the maximum amount of like chocolate chip cookies that you can. That's essentially what this is asking you to do. So what you would do is you would go and you'd say, okay, I've got this much flour, I've got this much chocolate chips, I've got this much butter, etc. And then you would figure out what the maximum amount of chocolate chip cookies you could make by whatever ingredient sort of limits the number that you can make them. So if you have a very small amount of chocolate chips, but you have a crap ton of flour and butter, ultimately it doesn't matter how much flour and butter you have, right? You can only make as many as you have chocolate chips. So you're sort of limited by whatever you have the least of. That's all a limiting reagent problem really is. And so that's what this question is asking. It's saying, what's the maximum amount of sodium chloride in water that I can make given what I have in my pantry? And so I come over here and I look at my pantry and I say, well, my recipe tells me that to make sodium chloride, for every 1 HCl I have, I also need 1 sodium hydroxide. So if I wanted to, let's say I think about the HCl. I'm like, okay, well, I have 3 moles of HCl. Does that mean I can make 3 moles of sodium chloride? And the answer is no, because I don't have enough sodium hydroxide to do that. I would need 3 moles of sodium hydroxide to do that, right? So it's like the sodium hydroxide is akin to the chocolate chips in that other analogy. And so I say, okay, well, I can't make that. Like, I can't make that. What's the max I can make then? It's going to be limited by the amount of sodium hydroxide I have there. So the maximum I'm going to be able to make is 0.7 moles. So what's the maximum amount of sodium chloride I can really make is just 0.7 moles. So what I would do is I would go into my pantry, I'd get 0.7 moles of, you could think about it this way, I could get 0.7 moles, of sodium hydroxide, and how much HCl would I get if I wanted to react that completely? Well, I would only need 0.7 moles, right? So then I would say, okay, well, if I left over in my pantry, I would have 2.3 moles of HCl. So I couldn't spend all my HCl. When I'm working through these problems in class, I'm doing them very fast because there's only so much time in a class. We can't go back and look at everything in detail that we've done in the past course. But I just say, okay, like we start with this much. Typically, you're not thinking of what you have in the product here. And then when you finish, you're just saying, how much do I finish with? Well, I know that since I know that this is the limiting reagent, because I've sort of just started out with my analysis saying, okay, well, whatever one I have less of is going to be my limiting reagent here because the stoichiometry is all 1 to 1 to 1. I know at the end that's going to be completely consumed. But I'm going to have some HCl left over because I just had extra of that. And so at the end, I'll have 2.3 moles of HCl. And then so over here, I'll have 0.7 moles of sodium chloride that I form. It will form some water too, but we don't really care about that in these types of problems. So that's pretty much like the neutralization part of the subject is just of these problems. It's just like you're looking at how much you start with, you're looking at how much you end with. So the next level on top of that is what is the, we would say like what is the pH? So if we weren't setting this up to be a very clear limiting reagent problem, instead of saying all that, we would just say, let me move this down a little bit. Here, we'll give it its own page. Okay. So if I wasn't making this into a clear limiting reagent problem, which is what I've done here, if we set it up that way, the way it would be kind of lumped into a normal problem we would just say, what is the pH? And I've left out concentration in this top example, just to keep things simple, but we would say like, what is the pH of a 1 liter solution formed from mixing well, let's say dissolving 3 moles of HCl and 0.7 moles of sodium hydroxide. So now we're asking a different question, but the starting point for it is exactly the same. So it's saying, okay, I've got 3 moles of HCl and I've dissolved it, and I'm taking 0.7 moles and I'm dissolving both of those in 1 liter of water. And so I'm trying to figure out what the pH is. And so you put the first question about pH aside. So I put that in the background because that's going to come later. And I start out working through things this way. So in order to figure out the pH, the first thing I have to do is figure out what I have left over once my neutralization reaction is done. So I'll say that again because I think it's important, is in order to work these problems where it's asking you, where it has a neutralization component, the step 1 is what is left over after the neutralization reaction. Neutralization doesn't have 2 L's. Neutralization is finished. And that's what we just worked in this top problem. And then step 2 is you consider what's left over and you say, well, I'm trying to think of how to phrase it. Let me work through it, and then maybe I'll come up with a better phrasing. Step 2 is to look at all the things that are present now and how they can affect the pH. So let's write down what's left over. So at the end of the neutralization reaction for this, my concentration of HCl would be 2.3, and I'm in 1 liter to make things convenient. So it'd be 2.3 molar. And my concentration of sodium hydroxide equals 0 molar. And in this one, we have a concentration of sodium chloride, which is just equal to 0.7 molar. And then I think step 2 is probably just looking at like sort of the components left over, which are important to pH. So remember, the pH is just all we're ultimately trying to figure out. Yeah, if they give you different than 1 liter, you just use you divide by the concentration. So you divide by the volume, moles per liter. That's correct. I just keep it at 1 just to keep the message on, I guess, like keep the messaging straight for the stuff that we're learning, the acid-base stuff. So for components left over, which are important to pH, so we can come back up here and look. Certainly the HCl is important to pH, right? Because it's a proton donor. Normally, sodium hydroxide would be important, but we don't have any left. We have 0 molar of that. So that's obviously doesn't really matter, right? That's like saying it might as well not exist. And then over here we have this salt, sodium chloride. But this is a neutral salt, so it doesn't contribute anything. So the only thing we really have to consider for the pH here is the HCl. And so now this bigger problem, which is what is the pH of 1 liter solution formed from dissolving a certain amount of HCl and a certain amount of sodium hydroxide, could be rewritten if we wanted to. The problem now becomes what is the pH of a 2.3 molar solution of HCl? Yeah, so then I guess I would say, like, step 3 is to use those components to calculate pH. So for a strong acid, which is what we're dealing with in this case, that's what your problem becomes, which is the pH of a 2.3 molar solution of HCl. And so I don't like these types of rules, but we can use them for halides, so group 7 or 17 or whatever we call it now. As long as it's not fluoride, you can see it as a spectator ion, it doesn't matter. Okay, let me finish this and then we'll talk about the molarity thing, because that seems to be a point of confusion. So HCl, so we're saying that this I'm going to call it group 7. I don't think that's the IUPAC term, but you know which one I'm talking about, the halides. So if it's a spectator, it doesn't matter at all. You don't even have to count it. So you can think of HCl as equaling H plus. And so really it's asking, when it's saying what's the pH of a 2.3 molar solution of HCl, it's saying what's the pH of a 2.3 molar of H plus. And so you just take the negative log of 2.3. So another way of saying this is that HCl equal to H plus. And that gives us some number, some low number. Negative 0.36, right? Okay. All right, so some confusion on molarity. Once you find the moles of what is left over, you have to divide it by the total volume again to find the H plus and OH minus concentration. The volume was not 1 liter. It just depends on how the problem is worded. Whenever you're finding, so remember the pH, So her question, Christine's question is, like, when do you? I think it's like, when do you use the volume? Like, how do you know when to use divide by 1 liter and stuff? It depends on how it's worded. So I'm giving it to you to keep things simple. I'm putting things in terms of moles. Let me come back up here and look at this. I'm saying I've got 3 moles and 0.7 moles, and I dissolve them in 1 liter, or I bring the solution up to be exactly 1 liter. So you know that everything is 1 molar because you're setting the volume at 1 liter. If you take 2 things that are different concentrations and different volumes, then your problem becomes a little bit more of a pain. So if I were to say take 500 mils or 1 liter, let's say I had 1 liter of let this go down some more. So let's say the problem was what is the pH of a solution made by mixing 0.5 liters of a three-molar solution of HCl with 0.5 liters of a 0.7 molar solution of sodium hydroxide. Yeah, now things change a good bit, right? So I think what I do for these is convert everything to moles. And then at the end, does it matter if it's the end? Let me think for a second. Let's say at the end of the neutralization reaction, you can convert back to concentration. And that is done by just dividing by the total volume. So there's a couple of, here you're diluting up to 1 liter and everything's going to dilute by half. You could do this in your head, but you could start out, I should use, well, you can see here you're going to get a different answer even though we're using sort of 3 and 7. But you know, you can convert that to moles. And then for sodium hydroxide, we can also convert that to moles. So you get 0.35 moles. And then you work through the whole problem again. You'd say, okay, you know, I've got sodium hydroxide, I've got et cetera, et cetera. In the end, what you should find is that you form, well, I'll write it out instead of just saying that. You'd say, okay, start with 1.5 moles of this and 0.35 moles of this. And at the end, call it the finish. We end up with 0 moles of this and 1.5 minus 0.3 1.25. Nope, that's not right. 1.15 moles of this, and you would form 0.35 moles of that. Then I would back it out, then I would put it back into concentration, because ultimately pH is the negative log. Yeah, you convert to molarity with the total volume. Total volume is something, it just depends on the problem. Ultimately, what you want, though, is the total final volume. Like, the final volume is the important thing here, because you're looking at the concentration of H plus in the final solution. So if I start out, if I'm mixing, if I have 1 liter and I add 20, like a concentrated stock solution to each one, so that, there's a lot of different ways you can do it. If I have 1 liter of HCl, so let me finish this one. So here you would take 1.15, and then your total volume is 1 liter. Total volume equals 0.5 liters plus 0.5 liters. And so you have pH is equal to the negative log of 1.15. So, pH would be really close to 0 there. But, the way you can ask these types of things is to get sort of arbitrarily large, or maybe not completely arbitrary, but there's a bunch of different ways we can ask it. You could have like let's say 0.2 liters of 1 molar HCl and 0.3 liters of 0.5 liters, 0.5, nope, can't have 2, 0.5 molar sodium hydroxide are added to 1 liter. Let me, just to get away from using 1 liter, let's say added to 0.5 liters of pure water. What is the pH? So in this case, again, you would just convert everything to moles, see what the reaction is, and then yes, your final concentration would require you to divide by the total volume. So it'd be your final volume is equal to 0.3 plus 0.2 plus 0.5. So you'd end up kind of working through everything and then dividing by whatever your final volume is. In the end, you just want your final volume, and it's literally just the sum of everything that you've added together to get there. So if you're adding 200 mils and then 300 mils to 500 mils, yeah, your total final volume is just the sum of all those different things. So I'm really not trying to get, I was not trying to get things to add up to 1 liter, but like it's just geared toward doing that. So here it all adds up to 1 liter. If you started out with, I'm trying to think if there's any other way to word these problems. This is a pretty common thing that you end up with, though. Just the pH, because the pH is equal to the negative log of H plus is dependent on the total volume. So, if you add a solution, if you add any liquid to it, any kind of solvent whatsoever, water, you're going to dilute the hydronium concentration. So this is something that you have to worry about typically when we're dealing with titrations. Yeah. Does that answer your question, Christine?
It was more of like questions if they ask for like a certain moles of a weak acid and a certain moles of like a weak base or like a strong base into like a 700 milliliter solution.
Okay. Oh, are you
So
asking if Sorry, go ahead.
Yeah, so if they're giving you like one like volume of the solution rather than like volume of each like each acid or base that you're putting into the solution, would you divide the solution by two for each solution to find the molarity
Oh, I see what you're saying.
instead of like if you're given 700 milliliters, would you do this times 700 milliliters to get the moles?
No, 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 no. So yeah, so if they're like, yeah, if they're like, you've got 2 moles of HCl, and I want to make sure I got your problem right, and like 2 moles, or let me put a different number, and 3 moles sodium hydroxide, and it's dissolved. I think you said 700 milliliters.
Yes, this is like exactly this kind of problem.
Yeah, what is the pH? So here, you assume that dissolving the HCl in the sodium hydroxide doesn't affect the final volume at all. And so your final volume is just equal to 700 milliliters. What's the concentration of HCl? So you're asking, I think you're asking if you like divide the 700 in half.
Yeah, so like even if it wasn't moles of HCl or NaOH, if they're giving you like a molarity and you're trying
Okay.
to find moles, would you have to divide the 700 to like for each solution to find the moles of the solution? Or do you just use the like total volume to find the moles if you're given like molarity of each
So
acid?
if they give you molarity, they have to tell you specifically how much of each molar solution. Um, Let me think about how you could phrase that. Like if they were say you take a 2 molar and a 3 molar, they have to tell you how much of each solution you're using. You
Okay.
couldn't say like I have a 2 molar HCl and a 3 molar sodium hydroxide solution and I'm dissolving that in 700 milliliters. You'd have to say I'm taking a certain amount of each one.
Okay, so they'll never give you a problem like that.
It won't be in molar. Yeah, yeah, they wouldn't say like if you change this to this, um, then the problem, this doesn't make any sense anymore. So like because these are concentration units, so I'm trying to think of like something that would be familiar that's not chemistry. It's like if you're making a like a mixed drink or something, and you want the total, like let's say, oh, man, mixed drink, is that a good example? Yeah, let's say that you're like diluting it for whatever reason. Um, it would be like saying like uh, take like vodka and triple sec and add it to let's say 700 milliliters of water, and we could say, well, what is the alcohol concentration of the drink? And let's say that alcohol, vodka is like I think typically 50% alcohol. I don't know what triple sec is, but let's say like 15% alcohol. Like what's the immediate thing that comes to mind here though? Like, do you understand the question? Like if I say like put vodka and triple sec into 700 mils of water, how much alcohol is there in the drink? What is this dependent on?
Wouldn't you just add the percentages and then times it by the total volume, like after you change into a decimal to get the total, like whatever amount volume of alcohol would be in the total volume?
Think about it. So I give you a bottle of vodka, and I give you a bottle of triple sec. Okay, and like let's just forget about the fact that they're 50% alcohol and 15% alcohol. Like remove the math from your brain for a second. But they have each one has a certain amount of alcohol in it, right? And I say, here is a jug of, here is 700 milliliters of water. Right? This is a strange situation we find ourselves in, but I give you this 700 mils of water and I say, okay, add vodka and triple sec to it, and then tell me what the final concentration of alcohol is in the drink. What is the missing piece of information that I need to give you?
How much
Yeah.
alcohol was put in?
Yeah, the moles or like
Or
how.
just, yeah, or just how much alcohol to put in at all, right? Like, so I guess what I'm saying is if I were to tell you, if I were to give you a glass of water and say, here's a bottle of vodka, um, like put vodka in there and tell me what the what the alcohol amount is going to be in the drink, you would say how much vodka to put in, right? Like you need to know how much vodka to put in. Does that make sense? Like you can't
Yeah.
just say, that's the equivalent problem of saying 2 molar HCl into 700 milliliters. You're not saying how much HCl you're putting in. It just has a concentration associated with it.
Yeah, I think I get it now. Yeah, I think
Okay.
it's the whole like molarity and stuff. Like, I get it now. Thank you.
Yeah. No, it's confusing. I was, as you were like asking, like once you work in the lab for a long time, like several years, then this stuff starts to become like a lot clearer because you have an idea of like you've done this practically. But like outside it, not doing it in the lab, it all kind of just sounds like, you know, jargony crap. Like molarity is not something you're really familiar with. So, but yeah, it has to be in moles. Moles is like a quantity that you can dissolve and get a concentration. If they give you molarity, you have to be given a volume. If they don't give you a volume, it's like giving you a recipe without any quantities associated with it.
So we would divide the moles by the total volume to get.
Yes, yeah. You're all in the end. You're always looking at total volume. Like when you're trying to find the pH, it's always linked to the entire volume that you have. So you just got to be careful that you add up everything that any volume increase from adding anything to it should go into the total volume number that you use to calculate your pH. So, ultimately your final, like your pH is equal to the moles of H plus over like the total, I'm kind of redundant here, but total final volume. And so this number includes any additions of any liquid or solvent or anything to it in order to calculate the pH. So you just got to keep track of it. And like we haven't really dealt with that. I mean, we see it pop up in some of the problems. When you get to titrations, that becomes more important because you're constantly diluting the H plus as you go through, and it kind of makes things confusing. So I have a meeting in like 3 minutes. I got to wrap this up. See if you can work through this problem, and then try to do the real problem that we're trying to get at here is what is the pH? But the workflow for the problem is the same as the problem we just worked, right up until you get to the point where you need to find the pH, because then you have to start messing around with equilibrium values. But if the only point of confusion is neutralization reactions, then everything that we did up here applies to this problem here. It can't get much more complex than that. I guess the one thing that can get a little bit confusing is if there is a confusing part, it's this part here, which are important for the pH. That's the part where you have to use some chemical intuition to figure out what's going on. So you have to be able to recognize, if you've got a neutral salt or a basic salt, if that's going to be important and contribute to the pH at all. So that's really, if you're getting stuck somewhere, this is really where you want to be getting stuck. This part and this part is something you already know. And I'm not saying like I'm saying like those are pieces that if you're following along should be kind of straightforward, because the first part is a stoichiometry part, and the third part is just figuring out the pH of a solution, which we've been over. The neutralization part should be getting confusing for you is this middle part. It's just figuring out what is important for the pH so that you can go on to step 3 and actually sort of do some calculations there. So, all right, let me rush out of here so I can get to this next meeting. You guys have a good Wednesday, and I will see you guys on Friday.